Institute. Today's speakers are both from the School of Maths and Statistics. In this session, if you want to get involved, you can use the chat box and there will be a Q&A part at the end of the session so you can ask the speakers. We'll also send you a feedback form and direct you to some free online courses on our Open Learn website. So without further ado, let me pass over to our two speakers, Kostu and Shomo. Thank you.
Thank you, Charlotte, and welcome everyone to our session today with the British Science Week, where we will be talking about fallacies in statistics. And I am Kostu Adhikari. I'm a lecturer in statistics. And with me is Shomo, who is a PhD student in the department working with me.
Hello.
So today we are going to talk to you about fallacies in statistics. And we think that this is a really important topic in today's world where we see a lot of data around, but also a lot of misinterpretations and confusions with the data. So today we will show you three examples, three very common and well-known examples in statistics where what we observe from the data can be really counterintuitive and confusing. So we will show you these examples and we will explain to you why that happens, what's the interpretation, so that in the end, when you encounter data in your real life, you'll be able to judge better what to do with those kind of information. So I'll start with looking at the first example, which is called survivorship bias. And this is a really famous example that comes from World War II when the British bomber planes were fighting in Europe. So these bomber planes were flying into enemy territory and they were often attacked by the enemy fire and many planes were damaged. So when these planes were being damaged, some were so badly damaged that they crashed into the enemy territory and were lost. So when that happened, the Air Force were losing a lot of planes, so they wanted to know how better they can reinforce their planes against enemy fire. So they conducted a study on the planes that were able to return after their flying missions to the enemy territory. And they wanted to reinforce those planes, but reinforcing is expensive. And it also adds weight to the plane, so that increases fuel costs and so on. So they wanted to add armor to those specific parts of the planes, which would help the most in terms of making the plane safe for the bombers in their journey. So the question to you today is that imagine you are the expert being consulted. So if we showed you the damage plan of the plane, then can you tell us which areas of the plane should be reinforced with extra armor? And you can see the damage pattern of the planes at the Desmos link, which is given in the chat. So please go to the link, please have a look at the damage pattern of the planes and mark those areas that if you were the expert, you would reinforce. And also when you do the marking, please comment in the chat to tell us why you will reinforce those patterns. And then we'll have a look at your response and we'll discuss what we could do. So please go to the link and mark your responses. And it's also fine if you are unable to use the Desmos link. If we will continue the discussion and we will show you the damage patterns, you can also enjoy the session if you can't access the link. So let me show the Desmos page in which responses have started to come in, and some people are already marking their responses. So we see that this is the diagram of the plane, one of those planes, and the red dots are marking the areas in which we have seen bullet damage in the planes that have returned from their flying missions. And there are certain parts which have lots of red dots, and there are certain parts which don't have that many red dots. So let's see what your responses are. And then please also put your comments in the chat so that we know what you think about marking these regions. So Shomo, since you are with us, why do you think that some people could mark the red areas that are marked on the plane's wings?
Well, I do agree with those markings because I think it makes sense to reinforce the areas with maximum bullet damage. We should shield those places where the enemy tends to attack more often.
Yeah, thank you. And do we have any comments in the chat, Charlotte?
We're just waiting for a couple of comments. I think somebody has said that you want to reinforce the bits that haven't been hit.
That's interesting.
Yeah, so that's a bit different to what Tim said. We'll just see if we can get a reason for that.
Yes.
Anybody like to tell us why you might reinforce? I can actually see on the Desmos screen that a lot of people are circling the bits that haven't got bullets on.
Yes.
Why is that? Here we go. We've got something coming up on the screen, it looks like.
Yeah, that's interesting. I did not Desmos had that visibility in the screen. That's interesting.
Okay, so somebody has said, if you can read that, dots where there are not hits, because those planes that were hit there probably didn't return. Interesting comment.
Yeah, interesting comment. So let's move back to the slide and let's see what the experts were thinking and what the British Army were thinking. So the British Army were thinking, as Shomo said, to reinforce the areas with maximum bullet damage, like the wings of the plane. And still they consulted the statistics research group in the US. And in that group, there was a statistician named Abraham Wald. And he pointed out the argument which somebody was just mentioning in Desmos, that the bullet holes represent areas that actually the plane could take damage and still return home. So here marked in green are those areas on the wing. But the parts which doesn't have bullet holes, those are the parts where if hit, the plane would not survive. So probably those planes that crashed in the enemy territory had bullet holes in those areas. Was that we have a bias, and we have a bias because we are making decisions not on all the planes that went into their missions, but on a subset of planes which returned safely. We don't have information on the planes which went out and crashed. So we are trying to reinforce those planes, but we are instead trying to make our decisions on the opposite subset. So it's kind of like looking at the negatives of an image and trying to make conclusions based on that. So the argument was that there is a hidden factor which we are ignoring if you're just blindly looking at the pattern of the dots. And the hidden factor is the survival status of the planes. And that splits our total set of planes into two groups, one which survived and which didn't. And the argument, as some of you have correctly pointed out, is that we should really be thinking about parts which doesn't have bullet holes, because that's the subset of the planes that we are interested in, planes that didn't return. So this is the survivorship bias, and this explains that in statistics, we can often have counterintuitive results given the data that we are looking at, especially if we have a hidden factor, if we have a bias. So when we are making decisions, we have to think about those possible factors, those possible biases. And another example of that is Simpson's paradox. And I talk about all these biases because, for example, in this case, the bias was unconscious bias. But often, as we might have seen, especially in today's world with COVID and some people peddling claims about COVID medicines that actually don't work, like hydroxychloroquine, that there are actually people who want to purposefully use biased data. And that's a nice cartoon that we have, in which the head of the business says to a statistician before hiring him that there are lies, damn lies, and statistics, and we're looking for someone who can make all three of them work for our company. So that is actually why we are having these sessions, so we can make you aware of these kind of issues. So as a mock example, let's imagine that we are looking at a medicine which is being developed by a pharma company, and they want to treat people who are hospitalized with severe COVID. So they want to see if this medicine is able to cut down death rates in such hospitalized people. So the standard procedure is to do a clinical trial, and they are doing that by following this procedure. So they will split the hospitalized patients into two groups, and one group will receive the medicine, the other group won't, so that they can compare the survival rate in these two groups and see if the people who got the medicine have a higher survival rate or lower death rate. And that will tell them that the medicine is working. So let's imagine that the company did this trial and they got some data, and we know that COVID survival rates are different in male patients and female patients. So let's imagine that researcher A looked at female patients in the hospital and got some results. And imagine that the data looks like this if put into a table. So there are 100 women who didn't get the medicine, and 5 of them died. And there were 300 women who got the medicine, and 18 of them died. So, Shobo, what do you think is the death rate of people who didn't get the medicine?
So that's 5 out of 100, 5%.
Yes. And what about women who got the medicine?
That should be 18 by 300, around 6%.
Yeah, thank you. So what can we conclude by looking at this data of death rates comparing between different groups?
I'm afraid it looks like that the medicine isn't working for the females, as the death rate seems to go up if you take the meds.
Yes, that's unfortunate, isn't it? And at the same time, researcher B in the pharma company was studying male patients separately, and researcher B also got some results, which we can see in the table below. So in this case, there were 300 males who got the medicine and 30 of them died. So what's the death rate among them, Shomo?
So that's 30 out of 300, 10%.
Yeah, that's pretty simple. And what about the people who got the medicine? 12 of them died out of 100.
That's 12%.
That's 12%. So what can we say from the death rate in males?
It seems that the story is same for the males as well. The medicine doesn't seem to work. People getting the meds are clearly more likely to die.
Yes, it seems that the death rates in males are just double the death rates in females, but the trend is the same, that those who get the medicine have a slightly higher chance of dying from COVID than those who don't get the medicine. So that's pretty unfortunate. And it seems that the medicine doesn't work because the death rates were higher among patients who got the medicine in both groups. But when researchers A and B reported their data to the chief researcher, and the chief researcher wanted to see the aggregate results before he or she could make a final report to their bosses. And the bosses would really want to see some data that supports the medicine because they have spent so much money and time working on this. So when the chief researcher wanted to look at the aggregate results, the combined numbers for all the patients look like this, that there were 5 deaths in women and 30 deaths in men in this group. So in total, there were 35 deaths. And in total, there were 400 people who didn't get the medicine, and actually the same number of people who get the medicine. So if we look at this table in which there were 35 deaths out of 400, what is the death rate, Shomo, in those people?
That's 35 by 400, around 8.8%.
That is around 8.8%. And we see that 30 people in total have died out of 400 people who got the medicine. So what is the death rate among them?
That is 7.5%.
So what can we conclude if we just looked at this table?
That's a little bit surprising. The medicine didn't seem to work for each of the groups individually, but in the overall data, it seems that the medicine actually seems to work.
That is indeed very surprising, and that seems like paradoxical, isn't it? That in each of these individual groups, the medicine did worse, but when you combine the data and you looked at all the patients, the medicine seemed to do better. So that is known as Simpson's paradox because it's a statistical paradox, and Simpson was one of the first statisticians to mention this. So what do you think about these results? If they are counterintuitive to you, what do you think that could be causing this counterintuitive results, and what do you think we could do to fix this problem? Please let us know your thoughts in chats. And while we wait for people's comments to come in, maybe we can discuss with Shomo what he thinks about this.
So what I think is the two populations are not exactly the same. What I found is the death rates are different in two of them.
Yeah, so the problem is that if the chief statistician decided to only report the aggregate data, the people who are looking at the data would not really know that there are these different groups with different death rates, and actually the death rates are worse in those groups, right? So what should we do in those cases?
I
So
think
if So
I
if
think
I am a reader of a newspaper and I see this study being published which claims this, then as a statistics aware reader, what could I do?
it makes sense to report each of them individually.
Yes, indeed. Thank you. And do we have any comments, Charlotte?
Yes, so we've got one comment, a couple of comments on, they're talking about the data sets being different sizes and the populations are different. So it's not comparing like for like, you're not comparing the same thing. That's what a couple of people have said.
Yeah, indeed, that's fantastic. So that's exactly what Simpson said. So he pointed out a few issues that first of all, if we look at the aggregate data, the cohort is not homogeneous. There are two distinct groups by gender. And again, this is the hidden factor. In this case, gender is the hidden factor by which we should really split the data. And the second thing is that females really have lower mortality than males, about half. So there are differences in those two groups. And also, as someone pointed out, that there is unequal allocation. The majority of the people who got the medicine are females, and majority of the people who did not get the medicine are males. So when you put all of these together, in aggregate, fewer people die after taking the medicine because most of these are women who in general have lower mortality. So in short, this could be summarized by saying that the less effective treatment is given mostly to the less severe group. And this imbalance makes seem the treatment to have a less severe effect as well. So that's the explanation for Simpson's paradox, that there has to be this distinct groups, and these distinct groups have to have different trends in mortality and unequal allocation. So that is an example we saw with COVID medicine, and that can happen in all sorts of other situations as well. The third paradox we're going to look at is called the false positive paradox, and we will also illustrate this with a mock example, in this time for a COVID-19 diagnosis. So imagine that we have an RT-PCR test for COVID-19, like the test that we have been using, and imagine the test is pretty good. So it has a false positive rate of just 5%, which means that it gives a true uh, so it gives a true negative result 95% of the time, and that's called the specificity of the test. It's very specific. It also has zero false negative rate, which means that if people who are infected, it will always diagnose them as infected. So it gives us 100% true positive rate, which means the test is 100% sensitive. So it's a pretty good test, but is it fair to assume that the test results can be considered as accurate everywhere? So we ask this question because we can have different scenarios. In this case, for example, take two different countries with quite different infection rates. US, say, has an infection rate of 40%, and New Zealand has an infection rate of just 2%. So if we had these two countries, will the test perform the same in both places? So please go to the Desmos link and go to the next slide. So you will have a yes, no button. So please let us know your responses in Desmos, and also please comment in the chat to share what you think, whether the test will perform the same in both places, will it be equally accurate in both countries. So please go to the Desmos page and let us know. So we have started to get some responses in Desmos, and it seems pretty neck and neck so far. And if you are putting your responses in Desmos, and even if you can't, please let us know your comments in the chats, in whichever medium you're joining us with. I see that no is slightly doing better. That's interesting, but please let us know what you think so that we understand why you said no. Okay, yes is gaining ground, but yeah, no is increasing as well. It's quite interesting. Thank you everyone who is responding. Very interesting that they are going up both.
Looks like a few people are changing their minds as they think about it.
Changing their mind. Interesting. So do we have any comments, Charlotte?
Couple of people aren't too sure. And somebody said, is it like the last one, different sets of groups, different samples? So is it similar?
Yeah, so the question is that, yeah, the two different groups, of course, are different with different infection rates, but the test procedure is exactly the same, and it's a pretty good test with high sensitivity and high specificity. So is there any reason to suspect that the test will perform unequally in the two countries? So let's go back to the slide since we have quite a few responses, and let's see what statistics tells us. So let's look at the example of New Zealand, and let's imagine the tests are conducted on 1,000 random people. If the infection rate is 2%, that means that most of these people are not actually infected. But in this situation, if we are just thinking about New Zealand for a moment, let's forget about US. So we have seen from the previous slide that the test is 95% sensitive and 100% specific. So overall, what will be the accuracy of the test in New Zealand if we started testing these 1,000 random people? So again, please go to the next slide on Desmos, and you will get a set of numbers. Pick the number that you think is most accurate representation of what you think will be the performance of this test. And again, please comment in the chat to let us know what you think. And I'll just go back to the previous slide to show you the numbers. So the test, again, as I was mentioning, is 100% sensitive and is 95% specific. And New Zealand has an infection rate of 2%. So please let us know in Desmos what your opinions are. Okay, so we have started getting some responses. So what would you say, Shomo, if we ask this to you? What do you think will be the accuracy of this test?
I think the accuracy of this test should be 95% only, since that is the true positive, the false positive, the true positive rate actually of the test.
Okay, I see. But that's among people who are actually infected. In New Zealand, most people are not infected. And the test is 95% accurate in those people. Or the other hand, it's 100% from a different measurement rate. So let's see what people say. And we are getting quite a few responses. Do we have any comments in the chat?
So somebody said that because the false negative is 0, but the false positive is 5%, then it only affects people who don't have the illness, and that in New Zealand more people don't have the illness, so therefore there'll be more false positives in New Zealand, somebody said.
Okay,
another person has said, I think the test will perform just as well, but the overall numbers will be different. So yeah, there's a bit of a mixed response.
Yeah, mixed response. And we see in Desmos as well, different people have different numbers, ranging all the way from 5% to 95%. It's really interesting. And thanks everyone for your feedback. So let's go back to the slides and let's discuss this more closely. So accuracy is a bit nuanced when talking about tests because there are many different metrics or measurements that measure the performance of the test. As we were looking at two numbers already, sensitivity and specificity, also known as true positives and false positives and false negatives and so on. So let's do a bit of number crunching, and you know already the statisticians really love tables. So we're going to put these numbers in a table and we'll see how we can measure accuracy. So we start by looking at the approximate number of infected individuals, and that's 2% of 1,000. So that's 20 people. The approximate number of healthy individuals, therefore, is 980. So if the test is 100% true positive rate, then all 20 infected individuals are correctly diagnosed. But the test has a 5% false positive rate. So among those 980 people who are negative, 5% of them will have false positive results. So that's 49. So the remaining individuals are currently diagnosed as COVID negative, which is true negative. So if we put these numbers in the table, we have a table like this. So show more, what's the total number of people who will test positive?
That's 20 plus 49, 69.
So that's 69 people who will test positive in total. And out of them, only 20 people are actually infected. So now we see that we have a problem, because in New Zealand, a COVID positive test will just be 29% accurate because in this case, we just have 20 out of 69 results, which are actually infected, but we have 69 positive results. So that's a problem in New Zealand, that a test which had such high number actually is having such low accuracy in people who have positive test results. So do you think this is surprising? Please comment in the chat to let us know what you think. And just to go back to the comparison with the US, if it had a 40% infection rate, then a positive test result will be 93% accurate, which is almost the same as the test performance we saw. But in New Zealand, with a low infection rate, it will only be 29% accurate. So please let us know what you think. And are there any comments in chat, Charlotte?
A couple of people saying it's surprising. They think it's strange. Yeah, but interesting, and you explained it well.
Thank you. So for the sake of time, let's move on to the explanation. And as we saw that the test, the biological process of how the test is conducted, everything is same, but the test is most accurate in the US, but can often be inaccurate in New Zealand. So that is known as the false positive paradox, as we were mentioning at the beginning. And the reason of that is that the chance of a positive test result is determined by two things, not only by the correctness of the test, but also by the characteristics of the population in which we are testing. So in this case, the test false positive rate 5% is more than the infection rate in the population, in this case 2% in New Zealand. So overall, we will see more false positives than true positives, or the true number of infections. So that is the reason for the false positive paradox. And this is important to remember when comparing different countries and different tests. So thank you for attending. I hope you enjoyed the session, and I hope you will remember these examples of misuse of statistics, because as we have seen last year, there were many instances that we had misleading statistics and misleading reports around COVID. We also saw some great work done by pharma researchers, for example, the COVID vaccines being discovered, but also there have been some dubious claims. In general, we always have to balance the good work and the bad work by not just pharma companies, but any person who is talking about statistics, be it in our real life or be it in statistical examples like you saw. So thanks for attending, and I look forward to any questions if you have. I and Chomo can answer those. Thank you.
Thank you, Kosta. That was really, really interesting. We're just waiting for some more questions to come in. The first one is there another example of Simpson's paradox in a different context?
There are many examples. A real life example is from the University of Berkeley, in which they were looking at admissions data and gender balance. And they saw that if you split by departments, and different departments have really different admission rates, then there would be uniformly low rates in, say, maths among both males and females, and say uniformly high rates in English between males and females. But the number of people who applied to different departments were very unequal. So when you combine the data, it looked like there was a huge gender imbalance, and women were having really low admission rates. So this is in one case as well, when Berkeley asked one of their statistics professors to investigate, and he published a paper actually detailing this instance. So there are many examples of Simpson's paradox in real life. even medical examples like kidney stones and treatments.
Thank you very much. Okay, and what's your most surprising statistical fact that you've seen in the newspaper that's sort of been a fallacy, or one that's stuck with you?
Oh, there are many, but if we move slightly from paradoxes, there was this report that women sprinters are going to outrun men by 2156 because there is a sharper decreasing trend in their best times over the years than men. And of course, widely extrapolating from present data is always risky. And we actually saw the exact same problem in one of the COVID analysis. And I actually did another session at the OU about it, in which they were widely extrapolating to say that 19 million Brits have already had the vaccine, had the virus, as I was showing on my slide. So all of these are problems with statistical extrapolation, and there are just too many problems everywhere.
Okay, well, I think we're just about out of time, but thank you very much to both of you for a really interesting talk. I hope that everybody enjoyed it. We're going to be sending you a short feedback form, and within that, you're going to have a link to Open Learn and also a reminder about other events as part of British Science Week. So thank you very much to everybody for coming along and getting involved in the chat box. We really hope you enjoyed it. Thank you.
Thank you.
Thank you.